don't have to consider those. Your branches for the recursive functions, right?
It's very cool.
So you can simply implement those inner or transparent. Right? Those are not considered. Now, so that means you only need to consider three parts of this project. The first one is to compute intersection. So intersection between the grids and the spheres and spheres. Remember, we have three objects, two spheres and one square on the pole. Okay? So that's the intersection detection. Then the second one to consider is the shadow detection. This one, right? Now the third is to compute the shading, right? Remember, the shading includes diffuse and also spectrum. So we have two types of reflections. One is diffuse, the other is spectrum, right? So once you compute the color for every point which is visible to the viewer, then that's it for that pixel, right? Then you can go to the next pixel or next screen, right? You don't have to check the mirror or transparent, right? So that's why this one is called the recasting instead of retracing. This is the recasting approach, right? So if you look at the sample code I provided in your project, alright, you can see
the actual retracing.
so we have two spheres defined by this center and this center x, y, z. Right. Of course, you can change those two centers if you want, right? And those are two centers for the spheres. Okay. Now for the retracing or trace ray function, there's a box. This one is used for recursive retracing. So in this project, since it's recasting, but you only consider the primary release, you don't consider the secondary release. So you can simply ignore this one, the bounce function. Right? You don't need this one. And also, there's one thing you have to be careful about, because in this render, we are computing the origin, viewport, and the VP and so on and so forth. So those are three-dimensional vectors, right? So we have a partition between two, three D vectors. This one is something you have to implement, right? Also, we have an dot product. This is a product between two vectors. This means it's going to be a product between two vectors, right? So here's what we do. So you can simply rewrite this statement. So this one is just a simple statement for vector operation. If you want, you can break this one into three statements. One is origin dot x, right? Or if you want origin underscore x, that's going to be x component of the origin vector, equals to. So this is a viewpoint underscore x, right? So you can break down everything into three parts. So that's going to be x, then you have y, you have z. Right? So you can do this in this way, right? By using the scalar for each component of the vectors, you can replace this single statement with three statements. Right? So that's one way. Another way to deal with the vector operation here is to define the partition of two vectors, or the dot product between two vectors, right? So you can define this x plus y, right? This one is going to be x dot x plus y dot x, x dot y plus y dot y, then x dot y. So this is the vector, right? It's a 3D vector. So you have to redefine the operator for partition and dot product, or also the scale, because we have, for example, let's see, this one here. So this is the scale vector. So if you multiply the scale vector with this vector, then it's going to be scaled vector for each component of the vector. Okay. So when you find the partition, scale, and outcome, then you can basically have this compiled property. Otherwise, you can see some compiling errors. Okay. So this is the one way. This is probably the simplest way. You can just simply replace the vector operations with x, y, and z. 3 statements, right? So that's one thing. And last one, which is tricky in this project, is the ray sphere intersection. So let me bring up this slides we have. Right, so this one. Now let me go through each one of the equations here, just to make sure you understand your every detail here. Right. Now in this ray sphere intersection, we assume the sphere is given as a radius 1. Right, so the radius of the sphere is 1. So it's a unit sphere. We also assume the center of the sphere is exactly the same as the origin of the system. So that means we're going to have a 0, 0, and 0 for the center. Right, just to simplify this calculation. Now the ray is given by P, starting from P. Remember, P is a 3D vector. That's a prediction of the starting point of the ray. Okay. We have the gradient of the ray. Right. This gradient is given by D, which is a normalized. Right, D is normalized. It's going to be D equal to 1. Right, normalize the gradient as 1. Okay. Then if you extend, you're going to see the intersection between the ray and the sphere. Right. So the problem here is to compute those 2 points as your intersection point, right, between the ray and sphere. Okay. So now in this, on this slide here, we have a couple of equations here. So the first one, T sub A, which is the product between the point P. Remember, P is this vector, right? Because P is a prediction, right? When you have a prediction, that means it's going to be a vector from the center to the point, right? So this is the vector P, right? This is vector P. Now D is this vector. D is this vector, right? It's direct. Right. So if you do the dot product between the two, there will be the projection of this point onto this straight line, right? So that is P start with D. You can take the absolute value of this one. Remember, this is a scale, a scalar function. That's a dot product that gives you scalar value. So take the absolute value of this one. This one will give you exactly this one. From this point to this point. Okay. This gives you P dot product D. Remember, both are vectors. Take the absolute value. Right. Now, since P is in this direction, D is in this direction, they are opposite to each other. So that's why we have this negative of P dot with D, because P dot with D is a negative value. The direction are greater than 90 degrees. Okay. So this equals to minus P. Right. So this is a Tm. Tm is this length scale between this point and the middle point from this part of the intersection between the ray and sphere. Okay. So that's a Tm. Right, it's a scale, right? Scale vector. Now Ln is simply the distance between the center to this point, midpoint. Yes.
Sorry, I have a question. So when we're calculating Tm, we're actually doing the dot product.
Yes.
Is the angle between
angle this one?
Okay.
Yeah, that's the angle. Right. Or this one can also be treated as a cosine of this angle. Right, cosine of this angle. is the scale of the amount between the vectors. Okay. Right. So LM is the distance from the center of the sphere to the midpoint of this arc here, the segment. Okay. Now, once you have LM, remember this is given by this one. This is given by P. Remember, this is the length of P. Right, length of P. This one is simply log P with itself. Take the square root. I will take this as 1/2. Right? So P log with itself will give you the square of the length of the segment of the next segment. That's why we take the square root of P log with P itself. So this one is simply the length, the square of this. Okay. Now you can compute area, right? Because we know this is a 90 degree. That's perpendicular, right? So that's why we have an area m square equals to this square, which is the P double with P, right? Minus this P double with P. Right? So that's why we get this one here, right? So we have area m square. Now once you have area m square, then you can compute delta T, because this is 1. That's the radius of the sphere, right? So this is 1, this is area m. Then you can compute this delta T. This is delta T. Then you have delta T equals to square root of 1 minus area m square. Get delta T square. Right? So this is how you compute delta T. But remember, delta T here is a scale value, right? It's a scale value because it's a simply root square, right? So you have a delta T, you have a P, right? You have a bracket of the grid, which is P. You also have this T. Then you can compute this point and this point. So what you do is that we first compute this point here, the midpoint, which is a P plus Tn multiplied by P times P, right? So this is the P starting point. This one is Tn, right? So P plus Tn multiplied by D. D is a derivative times D. So this is the vector, this is the vector, and this is the scale. This is scalar. Right? So you can say 3D plus scale times this is 3D, also give this to the vector. And this one is this point. That's this point. Right? Now you know the middle point is given by this one. If you modify half of this vector, which is this vector here, then you get P1. If you minus or subtract this one from here, then you get P0. Right? Now since this is given by delta T, then that's why we have this Pn plus Tn times Pt, right here, this point here, plus square root of this one. Remember, this is a delta T. So plus delta T times D will give you this P1 vector, right? Now if you take minus delta T times D, then you get P0. From here, this is the vector because it's a point. Right, so say we have a vector with a scale value. Sometimes we have a T as a scale value, sometimes we have T as point. So this T0 or T1 are points with the three vectors. Right. So this is how we compute those 2 points, T0, T1, those 3 intersecting points. Right? But remember, when you compute this one, underneath the square root operator, we have so P times D square minus P times P plus 1. This one here, if this is greater than 0, you have a 2 intersecting point because we have a plus and minus, right? Plus and minus of positive value will give you 2 different points, and those are 2 intersecting points. So we have a 2 intersecting point If this equals to 0, you have 1 intersection point. If this is a negative value, then you have a no intersection point. Right. So by checking this number, this value here under the square root, this value here, then if it's greater than 0, you know we have a 2 intersection point. If it's equal to 0, that's going to be like this one here. We just touch the surface of the sphere. That will give you just 1 intersection point. But if this is a negative value, then it's going to be like this one here. We don't have any intersection. So that's going to be no intersection between the ray and sphere. Okay. So by checking the sign of this value here, you can decide how many intersection points you have. Right. Now this is a standard case. Just follow those equations. By assuming the center of the sphere is the origin of the system, the radius is 1, is a unit 1. Okay. In this project, we also assume the 2 spheres given are unit spheres. Right, so that's going to be the same as this one. But the center of those 2 spheres are opposite. Right? So that means we have to do something to change the value, to change the formula here. Because we assume the center is origin in this on this page. But if you have an arbitrary center, we have to do something different. So this is something I want to explain here. If you have a sphere which is given as an arbitrary center, let's say we have C0, right? That's different from origin C0. Now we cannot simply follow this equation or those equations because that's going to be different from the origin of the system. Right? So what you do is to convert this arbitrary sphere onto the origin of the system. So you have a 0, 0, 0 here. You translate C0 by subtracting 2 C0. Right? So C0 minus C0 will give you 0. So you're going to have a sphere translated by C0 minus C0. You then convert the general or arbitrary center to this center. Okay. Of course, when you do this transformation, everything should be transformed, right? The same. So the starting point P, the derivative D, the way should also be transformed, right? Should be translated the same way. So that means this one will be translated here. This is a P point, right? Now P becomes P prime. The translation vector is the same. So this is the minus C0. But because everything is transformed the same. Okay. Translate P into P prime using minus C0. Right? So we have a P prime. Now the D here, since D is the derivative, so we have the same derivative. It's not changed. So you still have D, the vector D. Right? Now we have another case. Take the standard sphere, which is centered at 0, 0, 0. Give the P prime with derivative D. What's the intersection point? So that becomes exactly the same problem here, right? So just compute the intersection point here. T0 prime, T1 prime, right? By following the equations on this page, you get T0 prime, T1 prime, right? Then you have to go back to the original location, right? Then T0, T1 has to be computed from T0 prime to T1 prime, right? So here's the 3 steps you have to do. First, P prime equals to P minus C0, right? So that's the transition. Then second, compute intersection with P prime and P. Remember, you can see we're using P prime, right? But E is the same as original direction D. That's the same. P prime E and sphere. But the sphere here is a translated sphere, so it's 0, 0, 0. Right. It can be 0, 0, 0. The same gradient is 1. Okay. The third step is to transit back to T1 and T0, T1. Okay. So this will give you T0 prime, T1 prime. Right. Then you get T0 equals to T0 prime plus C0 and T1 equals to T1 prime plus C0. Right, so those three steps should give you the correct answer. Right. So that's how we deal with the spheres with arbitrary centers. So this should be all about the intersection detection for this. But there's one more thing. This is only the ring and sphere intersection. We still have a sphere, right? Remember the rho is given as a sphere. So if you have a sphere, right? In this case, you can define a sphere in a very simple way. You can define a sphere on x, y plane, right? So think of this one as x-axis, this is the y-axis, and then you have a z-axis perpendicular to x, y plane, right? So you can simply draw. It's up to you. You can maybe define the origin of the system in the center of the sphere, right? This is your x, this is your y, right? So you can define this as maybe 10 by 10 or your whatever size you want for the sphere. Okay. So if you define the sphere this way, the intersection becomes very simple, right? You have a P, you have a P times E. Remember that's the equation for the ray, right? One starting point, that's the origin of that's actually the viewpoint. Okay. D is given by the direction from the viewpoint to the pixel on the image, right? So if you consider, for example, the viewpoint, right? So that's our viewpoint. Then you have the image frame. Now let's consider just one pixel here. Let's consider one pixel here. We have an object here, right? The object is the sphere. Right? The sphere is on the floor. Okay. So generate the plane by connecting the viewpoint with the pixel here. So this will go to the space, right? Go to the space. So this is your P, starting point, right? And this is your P. Of course, you have to normalize P, the vector. So how we compute D? P is simply the point on the image plane minus P. That's correct, right? If you have this point here, we call this as Q, right? So P simply is Q minus P. Divided by the length of Q. Right. That's one point in the spin space. Minus P. That gives you the direction from P to Q. Then normalize by dividing the vector with the length of the vector. So we have normalized. So this is how you generate the plane. Now P is given. D is also computed for a specific pixel. Right. The only thing is this P here. You can compute it in a second. The only thing you have to figure out is P. What's the P? Right. Now remember this is a memory. this is t. Right. So t equals to 0, that's going to be the starting point. T equals to 1, that's going to be the unit length corresponding to 1 t. This is the t equals to, right? So if you want to compute the intersection, you only get to find out t. Okay. So I'll give you the rate, give you the square, how do you find out t? Because once you get t, then if you plug in t, then you get the intersection point. Right? So if you have the rate, you have this rate here, starting from p with the direction t. You want to find out what's going to be the intersection point between the rate and the sphere. Right? Remember, if you define the square this way, that means z equal to 0, right? Because from x, y, so z is always 0 if you define the rate this way. Okay? So if z equals to 0, then you can compute t. That's because px, remember px sub x equals to px plus t times px equals to 0. And this one is that's this is z. So z component of p plus t times d component of d equals to 0 because this is 0, right? Z is 0. Right? Remember, p is given, so this can be t equals to minus pz over pz. Right? Oops. The other way is the pz. Right? So pz over p something. Right? So that's how we compute t. Right? Then once you have t, then you plug in this equation here. Then intersecting point is intersecting point equals to p plus this is t. Let's say t intersecting times d vector. Right, so that's how you compute this intersecting point between the rate and the rectangle. Right. Of course, this process depends on how you define the square. If you rotate square into y and z plane, then x will be 0. Then you can redo this one, right? Like kind of t. Right. So this depends on how you where you place the rectangle. But this is probably the easiest one. Just make this one on the xy plane, you can get t. Then plug into this equation for the rate, you get the intersection point.
Just a question, what is that value right above the p at the bottom? The t next to dt? Yeah, just in the corner by the dot.
This one?
Yeah, I just is that t?
Oh, t equals to 0.
T equals 0. Okay.
So t equals 0 is if this is 0, you get exactly the starting point. Right? So that's the starting point. So this one is so p means t equals to 0. Right? The first point corresponding to the length of d means t equal to 1. And this one is actually 2 times d. So t equals to 2. Right, so that's how we define the t. We call this as a parametric method to model the rate equation. Then by using, we call this here as a parameter. Okay, that's a single line parameter because the rate is just one dimension. Right, so just one single parameter is sufficient to model. So that's actually t is a parameter values for this. Alright, so I think that's all we have for intersection. The rate sphere is given by this page and also this additional notes for that. And this one gives you the details for rate and sphere. Right? Well, 2 spheres plus 1 sphere. 3 objects in the project. Right. So what I want to do is probably 3 steps. If go back to the algorithm. This one here. So just do this in 3 steps or 3 versions of your code. Right. The first one is to start from the sample code. From here, you have to rewrite vector addition, vector scale, and dot up, and so forth. Right. So just try to do the intersection detection between the grid and the two spheres and the rectangle. Right. So this will give you, if you see any intersection between the grid and one of the 3 objects, then you assign one color to assign red to intersection. Intersection point, or maybe the black color to no intersection point. So this will give you one output image. Okay, this given by PDN. We have a sample to write into PDN format. So this will give you a sphere, maybe a sphere, or maybe a rectangle, right? Or in red color. And all sides are different. Right, so diagrams that color, the objects will give you just a single color, red color. And this one will give you the starting point of this project. You will have just final image, red color, red color, by just doing the intersection detection. Right. So if you are done with this step, I think, or the center, last time, this project will give you half of the work done because you will end up with this picture. Right. You have gone through the entire process except the second and third step. So the second version, I will say this is version 1. And version 2. Then you come to the shadow detection. Right. When shadow detection, you have to consider the secondary ray, right? So you have a primary ray from the viewer. You have a sphere. Just consider one object here, right? So this will give you the primary ray, right? Starting from the viewer to the object. So of course, if you don't see any intersecting, then that's it. You go to the next case, right? If you see any intersecting point, always pick the nearest one. Right, the nearest one to the viewer, because you may have the second intersecting point, you may have another sphere here, or you may even have the sphere behind. Right, you can say a number of intersecting points on the ring. That's possible, but always consider the one in the front, because all those intersecting points in the back is invisible to the viewer behind the object. So always consider the one as a nearest intersection point. Right, this is the important. Just pick the one with the smallest key, or pick the one which is closest to the viewer. So you can just do a simple calculation to decide which one is closest to the viewer. Right. So once you have this point, then you have to, in order to detect the shadow, you have to consider the secondary, which is a vector from this point to the light source. We'll put this as a secondary. That's a secondary vector. Now, this will give you another way, and this is going to be the same as the approaches we talked about earlier, except the starting point will become this one. So originally, the primary way start from P, have this direction P, right? this will become P. And this bracket from this point to the light source will become P. Right, so simply we define the rate by using the starting point at this second point here. Then the D pointing to the light source. So this will give you simply another rate. Then you just go through the safety tagging one more time. And say if there's any object, right? If you're saving with this way, if you don't save any object on this way, that means this point will be you're receiving the energy right from this source. Right? If you save any object here, that means this is going to be in the shadow of this light source. Right? Remember what the two light sources? You have to do this twice. One is for light source one, other is for if there's another one here. Right? Then we have to do this one, arrow 2 again. Arrow 1, arrow 2 is arrow 1. So that's the second ray, arrow 1, second ray, arrow 2. Just repeat this one for 2 times. Okay. So you can see we have to do this, and it's a 3 times intercept detection. First, primary ray. Second, the first light source. Third is the second light source. Right. So that's why I want you to probably have a subroutine for the intercept detection, because we will call this function 3 times. Right. So if you have if this point is in the shadow of this light source, then simply ignore the lighting from this source. Right. If it's not in the shadow, then this will move to the third step, right? The shading. Now we'll give you the actual RGB color, right? So this will give you RGB. So we have 2 types of shading. One is diffuse. We have a talk about this a lot of times. Diffuse, another is vector. So for diffuse, so let's say we don't have any objects here. Right? So that means this one is not in the shadow. We'll not consider the lighting for this source. Okay. So if this is the object, the vector to the light source 1, then we have to compute the RGB that comes from this light source. Right. Remember, for the diffuse, we consider the non-vector. So this is the center. For the sphere, now is very straightforward. Right? Simply connect, extend. That's going to be your normal vector. From the center to this point, right? Of course, we have to normalize this one. So normalize just 1. Right? Normalize the vector. Then the diffuse is given by n. And top is a arrow, either 1 or 2. Right? Then you have a K times. K is the coefficient of the diffuse, right? So simply take the upper route between arrow either 1 or 2, right? With the normal vector. Okay. So if the light source is exactly in the normal vector, now will give you the highest energy or intensity. But in general case, you have some angle. So the angle will tell you how much energy you save from the light source. So that's going to be by this one. Right. Now, spectrum is defined in the small angle relative to the reflected ray of the light source. So we have to compute the vector, which is reflected of the light source. Okay. This one is called R1. Right, R1. Then you have to consider R1. Let's see, the viewer. This is the viewer, or this is the viewer. Okay. V dot is R1 or R2. So R is reflected on the light source of the sphere. Then we have P is. Right. So those are 2 components. Okay, to simplify, you can consider the diffuse first and generate the picture. You always can generate the PDA by only consider the first stage, you have the picture. Then consider the shadow, you can generate another picture with a better, post better quality. Then you can consider diffuse, then generate the picture compared with the previous version. Right? Then you have the diffuse and scatter, then you are done with this. Right? Okay. So this whole process basically will test your understanding of the 3D lighting, right? The maths about intersection detection, and also some geometries about the relationship between the light source, the viewer, the objects. Right? So this is a very good process to understand the detail of this problem.
So are we manually giving it like the red color?
Oh, this one, yeah, it's up to you. I just use the red as example. You can use any color because remember the first two stages is not realistic, right? It's not realistic. We haven't received the actual color from the light source because we haven't considered the light source in the first two stages, right? So you can assign any color, red color or blue color, anyone, just to distinguish between the objects and the background. Okay, so that's up to you. But the last one, this is the actual color from the light source. So you have to compute using the diffuse spectrum models. So this will give you the actual RGB. Yes.
So then, did you want us to show you each version then?
No, you don't have to show each version. So this is just for your own purpose. You debug the code one by one, right? So first of all, you generate the first version. That will be probably giving you some confidence from the project, right? At least you see some picture, okay? Then you just add some more details into the program. Right? But the final submission will be just the final picture with the color of different settings and different permissions of the sphere, right? Or maybe different colors of the light sources, right? Or you can maybe change the relation of the light sources. Okay. Now, once you have all those details implemented, you can generate a number of pictures by changing the colors. Right?
Well, for the specular view,
specular shading.
yeah,
This is the PS times V. V is the vector from this point to the viewer. So this is actually the final rate. That's the V, right? And this is R1 or 2 because we have two light sources, right? So R1 is going to be, this is the light source 1. R1 will be reflected of L1 to the other direction. Number reflection is given by the normal vector, right? The incoming lights and also outgoing lights, those two angles will be equal. That's how we call this reflection on the surface. Okay. So if this is L1, this will be R1, where angle R1 equal to that. Okay. So they are separate, but the separation is going to be the normal vector of the sphere. So for the square, the normal is simply the perpendicular. There's going to be z direction, right? In our case, it's going to be z direction because we have placed the sphere on the xy plane. So it's going to be this z direction for the rectangle. Then for the sphere, the normal is going to be the vector from center to the point. Remember, always normalize the vectors for normal. Alright, so any other questions? Yes.
I just had a question about after the square root thing above. In the
that one?
yeah.
Okay.
In the algorithm, it shows that we're doing a dot product with D.
With D.
Yep.
Yeah.
But, so is
This
that
one?
yeah? So after we compute all that, the square root, we're just getting a scalar value from it.
Remember the dot product gave you scalar value.
Yep.
This also gave you scalar value. So that means the whole thing here is a scalar value,
Okay.
right?
Yep.
But remember, this can be positive, 0, or negative. Okay, this goes in here. Right. So before you compute the square root, check the sign of this number, right? Because that sign tells you how many consecutive points you have.
Okay.
Yeah.
And then we're doing the scalar value dot product with
No, P here is a vector. P and D are vectors, right? The dot product is always defined for vectors.
Yeah.
Yeah. So P, D are vectors because P is a location. Location is a three-dimensional x, y, z in three space, right? So P is a vector. D is a direction. That's also a vector.
Yeah.
Three dimensions. Okay. So the only I would say yeah, the scalar value here, Tn is a scalar value, right? Tn. Let me go back to the slides. Yeah. So Tn is scalar, Rn is scalar, because Tn is simply the length from this point to this point. So that's the scalar. Rn is a distance from this point to this point, that's scalar, right? Delta T is also scalar, right? But this is a dot product, but it is scalar. Dot product, it is scalar of value. And this is the square root, that's also scalar.
Yeah. So then just at the bottom function, why is there the dot product D at the end?
This one?
Yeah.
Oh, because this whole thing here, this one, square root, is the delta T. Number delta T is simply the length of the segment, right? If you want to get the point should be this point plus the vector, right? So it should be a vector added to a point, not give you another point, right? In other words, you have let's see. This is P plus Pn times P. It's a vector, and it's a scalar. That's actually this point, right? So if you compute this point here, what you can do is to add delta T times this direction here, and this direction convert is simply P. That's the same direction here. So times P. Right, so this is the length delta T. Right, so that's why we have to modify this length of the segment with the direction of this segment. So this will give you the vector from this point to this point. It's not here, it's actually this vector. Right, so this vector added to this vector at this point here will give you the endpoint. Right. And this is a minus, and I will give you this point. Right. Number 13 is actually this one. This one is simply the 13. Right, before the vector. Yeah, that's now this dot is actually not dot product. This is simply the scale of the product, regular product. Right. But this is scalar. That's a vector. Right. Yep. Alright, so is there any other questions on this project? Alright, so if not, I will go to the